Thank you for the welcome. So, as mentioned, I'm working with the John Adams Institute for Accelerator Science at the University of Oxford, and looking at evaluating the environmental impacts of proposed ICES-2 neutron and muon source. So that's what I'm going to talk to you about today. So, firstly, we need to consider why we need to talk about the intersection of physics and the climate crisis and why we need to consider that. And then I'll introduce to you what ICES-2 is actually going to look like, and give you a bit of background if you're not too familiar. And then I'll talk about my work on the environmental impact and the potential for a life cycle assessment at ICES-2, including the methodology and the preliminary results. So, in general, we can agree that the climate crisis is a problem. It's not going away, and as scientists, we are able to generally agree that there is something going on that we need to do something about. But why do we specifically, as physicists who don't work in that field, need to not just physicists, engineers, researchers, everyone who's in the scientific field? You can argue that we have a moral and social duty just to lead by example. But also you have to acknowledge that we are majority publicly funded. So we need to be able to justify our work and ensure that we are doing our bit to improve our environmental impact or reduce it. We've got some comments online about how we can keep upgrading. So, for example, in the particle physics world, we're asking for one more collider. And if we really look at that from an environmental point of view, we really this would really have a massive impact. So we need to acknowledge that, evaluate it, and see what we can do to reduce that. But what do we really mean by the environmental impact and by sustainability? Environmental impact can be direct, indirect, the resources we use, the biodiversity we impact when we build, that kind of thing. And sustainability as a quick, short definition, I leached off of Wikipedia, is a social goal for us to coexist over a long period of time on Earth. So multiple generations, allowing people to have a good quality of life, similar to that what we're able to similar or better to that we're able to live in today. But how does this really relate to our field? In general, our environmental impact is quite large and generally unsustainable. So if we keep using these resources, these could eventually run out, specifically gases like helium, which are becoming more and more rare. So the resource consumptive, and as we're growing in generations, our next generations of accelerators, they tend to get grow in size and or power, and therefore generally consumption. And as you can see here from this study, we as researchers have a large individual footprint compared to the average member of society. So around, can be up to 45 tons of CO2 equivalent per year, to the order of 1 to 5 per member of society who isn't a researcher. But there are many efforts going on around the world to reduce that. So we are looking at evaluating that through our carbon emissions and impact reports. So quite recently, there's been a few published by different facilities. We have then, with results of that, been looking at research and design for for reducing efficiency of machines, increasing efficiency of machines, such as our cryogenics that we use, reducing our resource consumption. So, for example, helium recovery or waste heat recovery. And we've been developing sustainability guidelines to follow and keep our actions going the right way. We've also been looking more into the individual researchers, so trying to reduce our individual impacts, such as for our air traffic. And there's many more where that came from. I don't have time to mention them today, but there's a lot going on in our field to try and improve our. So the ISIS-2 neutron and muon source is the proposed upgrade to the current ISIS spallation neutron and muon source at the Rutherford Appleton Laboratory, or RAL, you may know it by, which is in Oxfordshire, just south of Oxford in the UK. It is the world's only two-target pulsed spallation source, and it produces world-leading science just like you do here at ILL. This year marks our 40th anniversary since we started producing neutrons, and currently it is a 800 MeV synchrotron, and there's our two targets with all of our instruments around here doing our neutron and muon science. But with that, reaching our 40th anniversary, we're starting to reach the point where we need to consider the next upgrade as ISIS-2 comes to its end of life. So the ISIS-2 neutron and muon source is proposed to be a 1.2 GeV upgrade. There's multiple design options, but the main one we're considering is a new facility just next to the current ISIS. So that would allow some overlap between ISIS and ISIS-2 during construction for ISIS to continue running before shutdown and then ISIS-2 being put into commission. So we have up to an overall power of about 2.4 megawatts, dependent on the target technology we use and depending on our ring designs and other considerations. And again, it is going to be with two target stations. So the stage we're at now is our feasibility, design studies, and R&D. In our next phase, we're going to be looking at actual physics design and large-scale prototypes. Hopefully then to start building in around 2031, ready for users in about 2040. So yeah, that's where we're going. That's our rough timeline. So for our first target, we're looking at high repetition rate targets. So it'd be 30 hertz at 1.6 megawatt target. High resolution, same or better than what we have our current target station one at ISIS. We expect the gains to be proportional to power with a flux gain of about 10 over the current ISIS. And we'd be using decoupled water and hydrogen moderators. So this is a sample of what our instruments would look like around the target. The other target would be a low repetition rate, so that would be more focused on gold neutrons and high brightness. So that would have a rate of 15 hertz and 0.8 megawatts. This preliminary concept looks a lot like the current SNS spallation neutron source in the Oak Ridge National Lab second target station with a flux gain of about 70 to 100. And there are several options here for our neutron. Muon production, such as intermediate targets or standalone stopping targets. So again, this is our potential design for the instruments there. We are considering 3 different rings at this point in our design. We have either an accumulator ring, a rapid cycling synchrotron, or a fixed field alternating gradient ring. And I'll talk about more of those later because that comes into my study of the environmental impact. So then our project phase 1.2 B plan, so that's where we're heading for next. We'd be looking at constructing a small FFA test stand, or FFA test at our front-end test stand at RAL, which is currently already existing there, to explore beam dynamics. We'll complete our ring designs along with our LINAC designs that would go alongside those. And then we'd complete everything else, our target moderator, shielding designs, etc. for our different targets. And hopefully have an optimal concept design with credible initial cost estimates, but also an environmental impact estimate from me. So this is what ISIS-2 might look like. If you have been to or seen RAL Harwell campus before, RAL and RAL, ISIS-2 would be based at the south end here. So this is where currently ISIS is, and this is potentially where we'd put ISIS-2. So moving on to what I'm doing now, looking at what we think would be the environmental impact, so trying to model that. So firstly, we have to justify that what do we actually want to do, and why do we want to evaluate this impact? Firstly, we want to try and inform our design options. So I mentioned 3 rings. We're trying to inform that design, the choice of the 3 rings, alongside the physics reasons and the costs, also the environmental costs. We also want to just report on the full lifetime impact of the whole of ISIS-2, and then also try to identify hotspots to then reduce any like low-hanging fruit, but also just see if there's ways that we can optimize our designs to improve our environmental impact. And hopefully then that will lead to a development of some methodology just naturally that can be used by other facilities that are considering future upgrades. So how can we achieve that? What I've decided to do is to have 2 key stages to this analysis. Firstly, have one environmental impact of the whole of ISIS-2, and that's just more of a carbon footprint impact. And that would be all the core components of ISIS-2. Then also try to follow the ISO standard methodology for a full life cycle assessment. And now this is very complicated, so it would likely have to be a more simplified version, or maybe even just follow the guidelines of the life cycle assessment. But we're attempting to do a full life cycle assessment, and that will be to compare these 3 ring options to then inform our phase 2 bid, phase 1.2b bid, sorry. And with each of these rings, we would need a different LINAC to reach the power for the ring, depending on whether it's a storage ring or an accelerator ring. So a first disclaimer, like this is very early stages in this work. So there is also a lot of assumptions in this work. We're modeling something that hasn't been basically designed yet. We're still in the very early stages of ISIS-2. So these models are updated very regularly. And there's a lot of studies ongoing and future ones to come to make this study more precise and more accurate. So just a quick disclaimer then. The ISIS-2 components, as you are probably aware, have many of the most common components of accelerators. So we have our source and pre-injector, our LINAC compression rings, our extracting protein beam lines, targets, and our instruments, and then the ancillaries that go alongside those, flash rods, etc. So for our source and pre-injector, in my model, I'm assuming that we're going to use something similar to the ISIS H-penning ion source. And I'm modeling using the front-end test stand that's currently at RAL. But a interesting outcome of the study so far that I thought I'd share is that a perhaps low-hanging fruit in how we can reduce our impact is by machining our materials more efficiently. Perhaps, for example, I found in the RFQ of the front-end test stand, originally we had 16 blocks of oxygen-free copper, which came to about 4 tons of material. But after machining, we only actually had the RFQs equaling 0.8 tons of copper. So 3.2 tons was actually scrap, wasted, and sent to recycling. Now, naturally, because you're machining them in this way, maybe you can't optimize that massively just because you're removing the center, etc. But perhaps when you're talking to the engineers, we're able to reduce that machining wastage. So with our LINAC, we have our 3 options. So we'd have to, for example, have a low energy INAC with our 2 accelerator rings, so the RCS and the FA, or have a full energy LINAC up to our accumulator ring. So there's a few different designs of our LINAC design proposal. We also have a 4th option, which we're considering as a fallback option. So that would just be a simple upgrade, not simple, but an upgrade to the current ISIS LINAC up to 180 MeV. So in my model, I'm using ISIS-2 models designed by our designers, and but also using ancillaries that are currently used worldwide, such as supply strands, modeling them off, for example, ESS. But as a first example, looking at just the shielding proposed for the LINAC, we're looking at about 10 kilotons of CO2 just for the construction of just the shielding, not tunneling or anything like that, and assuming that the shielding is just concrete. For our compression ring options, we have, I've had a first look at the environmental impact, but to reach the 2.4 megawatts proposed for the full energy of ISIS-2, we would have to probably consider the idea of having stacked rings, but those would possibly be included as a staged upgrade path. So we don't start with the 2.4 megawatts and then have that planned into upgrades. For example, we can look at the RCS and the AR and say that the lattice magnet ring designs are identical, but the AC and DC operating between them, their parameters are different. So the power distribution would be different between them, but we can assume that the total power consumption is the same. So starting to delve into that more to try and figure out what the actual differences would be between the AR and the RCS. So that is what we'll be considering in the full life cycle assessment. Similarly, looking at the shielding there, we're looking again at about 10 of kilotons of CO2 of emissions. Again, with the extracted photon beam lines, looking at the shielding, this would actually go up to hundreds of kilotons of CO2 just through the length of those. I've been looking at trying to model our extracted photon beam lines using the SNS equivalent called the ring to target transport line. Yes, we're updating that as we go along. But just for a bit of more detail, but just for interest, the way I'm trying to model this is by starting off like top down and then move into the subcomponents as we go. So starting off with, for example, what an estimation of the shielding and then the magnets. But then once the information is available, then breaking it up and going into more granular detail with each of the different magnets. And hopefully what will be useful from that is that in the future, other facilities could use these same models to, for example, if they know that their magnet would have their quadrupole would have an aperture of a certain size, they can at least take those as a first model and either use them as a rough estimate or just update them to what they have in their designs. So that's where I'm hoping to go with that. For the targets, as I mentioned, we have two targets, a water and hydrogen decoupled moderators, but also in target station 2, we're considering top pancake hydrogen and bottom hydrogen rods. Our current design suggestions are either have a target station that's basically a copy of what we have at ISIS now, or we consider a 1 megawatt target station similar to the second target station they're about to build at SNS, or consider other options there. In the lifetime consideration, it's really important that we consider the lifetime of the target itself. So, for example, the target material, how does it react to radiation damage, and how often we have to replace it, actually would then obviously impact the environmental impacts just through replacement through the whole lifetime. So that's something we have to try to model, and things including failures and that sort of thing. And again, around 10 kilotons of CO2 just for the construction of the shielding target stations. And then this time, this is including steel in the center. Sorry, that's a bit small, but the green is concrete and the blue is steel and the orange is the void where the target would be. So trying to also evaluate the impact of the instruments. At ISIS-2, we're considering starting with maybe around 26 instruments, and perhaps by the 10-year mark of users, moving up to around 40, potentially. And recently, STSC succeeded in getting funding for the Endeavour program at ISIS, which is the upgrades to the instruments. And I'm using those as a model for the instruments that we're trying to use for ISIS-2, because we don't expect the technologies to change too much over the next decade or so. So I'm using a model for the Neutron instruments and a model for the Muon instruments, and cherry picking the more usual components between those. And yeah, trying to also predict how the data rate is going to change with the increase of neutrons, etc. And then try to potentially use SMS or ESS to help us model those. Again, can't forget our ancillaries, so things like 𝐋𝐢𝐿𝐿 and power sources. We have to look at the efficiencies of those so we can improve those. I'm using models trying to get that from that information from suppliers, but also where that's not possible, using current facilities such as SMS and ESS, as I mentioned. So studies there will be performed to determine whether we can get better ancillaries with our budget, etc. And these can then be considered in our design stages. It's important to note that concrete is one of the largest expectations in our construction impacts for ICES2. At this stage in the analysis, so as I mentioned, there's a disclaimer, it's very early in the analysis, but I'm predicting that the concrete construction is going to be equivalent or at least order of magnitude similar to the full power consumption of the whole of the lifetime of ICES2, depending on how well we decarbonize the grid, etc. In the UK. Yeah, therefore we're making some efforts to try to reduce the potential of the concrete impact and looking into alternate options, perhaps a greener concrete if that's in our budget, or alternatives like different mixtures of concrete. Potentially, there was one study trying to look at putting rubber into concrete to see if we could reuse tires and that sort of thing too. So some first numbers, a top-down approach looking at the CO2 consumption of the power intake at ICES2. We're expecting potentially up to a 30 megawatt facility, which is massive. And noting that we have a spare capacity here of about 8.5 megawatts. That would potentially, considering the UK decarbonisation of the grid for the next 60 years, which we don't have too much data on, that would emit about 600,000 tonnes of CO2 equivalent over the full lifetime of ICES2. And our largest contributions there would be our LINAC, our synchrotron, and our cryogenics, also including the spare capacity. In addition to that, we're also studying the computing impacts. So computing is notoriously one of the largest power consumers of high-energy physics and accelerators, etc. The study is ongoing for that, yeah, we expect that our computer requirements are naturally going to increase compared to ICES. We've also done some back-of-the-envelope calculations on travel, for example. So local travel, this would be our local employees and staff, based on a lot of assumptions, which I won't waste time going through. I calculated a roughly 2 kilotons of CO2 emitted just by local travel through driving to work, etc. And similarly, looking at our users, if we expect maybe the same amount of users, which we are not sure yet, we're still considering whether the number of users would go up. I think they would likely. And considering that currently our users are 25 international, the majority of them coming from Italy, the Netherlands, Sweden, and Japan, using just a quick Gaussian to try to estimate that, we can see that we'd probably get around between 4 and 5 kilotons of CO2 through our national travel users and our international travel users. Looking at decommissioning, that is actually more of a can of worms than you would think. For ICES2, we'd probably be decommissioning between 2100 and 2170. We in the UK have a decay storage limit of 70 years, so we can't store anything longer than that. In addition, in the UK, we don't have any long-term storage facilities planned for that sort of timescale. So currently we have something called Sellafield, I think there is one planned storage facility after that. but for the ISIS-2 timescale, there's nothing planned. So this would be something that we need to be in contact with the government, etc., with to make sure that that is available, or consider the other options. So we're using current ISIS modeling for our waste, the plans for decommissioning of ISIS itself, our expected amount of radiation, radioactive waste at ISIS-2, and also using other facilities such as ESS and their estimations on how they're going to decommission. But this is very highly dependent on each country and their radioactivity restrictions. But also, obviously, we are considering the non-radioactive waste as well. So how we're going to recycle that, whether that's possible, and what the impact of that would be. So again, some numbers. I already went through the power consumption, but as a very quick estimate in terms of our embodied carbon of our buildings that we'd need for ISIS-2, we're looking at around 100 kilotons of CO2 equivalent. That was a slight worst case scenario guess, or back of envelope calculation. I did one study on the tunneling for the LINAC, which I'm then going to extend to the rest of the areas that would need some form of soil maneuver. So we're looking again at 10 kilotons of CO2 there. And then a summary of some of the numbers I showed earlier, looking at the shielding materials for each of the facilities or each of the sections of ISIS-2 could total up to about 230 kilotons. So as you can see, we are starting to reach the 600 kilotons equivalent for the power compared to our construction at ISIS-2. So we've got a pretty good grasp of what the construction of the operation, and I have started to look quite a lot at the decommissioning at ISIS-2. But now we're also looking at the life cycle assessment of these rings that we need to consider and compare. So if you're not aware of what a life cycle assessment is, it has 4 main stages. So we consider our goal and scope, and then we basically collect all of the inventory, so all of the materials, all of the resources that we'll be consuming, the ins and outs of the lifetime of this facility, and then you do perform your impact assessment. So you see how that's going to impact the environment, and then you interpret that and try to see where you can reduce that and make sure that you go around and take everything into account. It's an iterative process, so you can go back and forth to try to make it more efficient and make more sense, and more it covers everything. And so this is what we're trying to do at ISIS-2. So for our goal, we want to evaluate and inform the design for ISIS-2 with a comparison of these 3 ring designs and the relevant LINAC to it. At this point in time, I'm spending most of my time just doing it between 2, so the RCS and the AR, just because there are existing models, large-scale facilities that exist that I can use to model those. So for a first examination, we're just looking at the 2. Initially, I'm using CO2 equivalent as our first impact parameter, but this is just as a first examination. I will be extending to the full environmental impact, such as, for example, biodiversity, toxicology, etc., to the environment. And the current functional unit, if you're aware of that, what that is an ISIS-2. So I'm comparing one ISIS-2 to another ISIS-2. But in the future, I'd like to develop that and investigate updating that to a more comparable evaluation so that it can happen between facilities. So, for example, if we're able to compare our CO2 for user hour, it can be something that we can compare. I mentioned this already a little bit before, but the inventory analysis is looking at the main stages of our lifetime of our experiment. So we have our construction, our operation, and our decommissioning, and it's a very much input versus output consideration. So as I won't go through that, but basically each of the key components, we're making sure that we take those all into account. And so how we're doing that and how we're performing the impact assessment is trying to follow the standards that exist already. There's also an engineering standard that I've been using as a slight guideline, which allows you to break down the different stages of construction, operation, and end of life, and to make sure that you've encompassed everything into that. And it's similar to the 3 stages of construction, operation, decommissioning, just a bit more defined. So I've altered the description of those to be a bit more applicable to large-scale facilities such as ours. And if you're interested, we're using the recipe 2016.H methodology for the impact assessment. And the software we're using is something called OpenLCA, so it's an open source software. And using a database that's free for academics called the IDMAT database. We are finding, or I'm finding at this moment, that it is very useful, but it is missing some key components that we use a lot at facilities such as gases and more rare materials. So at this point in time, I'm seeing if there's other available free databases. If not, maybe looking to pay for an industry standard one. And as I mentioned, a good outcome of this means that it would naturally create a database of key particle accelerator things, such as magnets, that can be used by other facilities. So with that, thank you for listening. I have been looking at evaluating the environmental impact of sustainable environmental impact of particle accelerators, and trying to reduce those fundamental research. ICES is the next proposed upgrade to ICES 2 in the UK. ICES 2 is the next proposed upgrade to ICES in the UK. And we're looking at evaluating the environmental impact of the whole of ICES 2, and then performing a life cycle assessment of the rings to inform our design options for our next funding bids. So yeah, thank you for listening.